In this lesson, I will present some strategies and hints for solving applied problems. My first advice would be to read the problem at least twice, or as many times as many you need, to understand the problem fully, recognize some patterns, and apply strategies that you may know. After you read the problem a few times, you will most likely be able to recognize some sort of type of problem, refer this problem to something that you already know or experienced before, and draw appropriate tables or diagrams to organize your data in a useful way. So organizing data is very important before you start writing any equations. At that stage, it's a good idea to list any relevant formulas that come to your mind. Now it's a time to assign variables. Usually you assign a variable for what the question asks. Also, my suggestion would be to use meaningful letters for a variable. It doesn't always have to be X and Y. If it's time, it's a good idea to use T. If it's number of nickels, maybe it's N. If it's about number of adult tickets, maybe it will be A for adult. Just use meaningful letters so it will be easy for you to recognize what is that you actually solved. Finally, when we already have the variable and the data organized and some relevant formulas, it is time to write equations. You write equation either by following the formulas that you already have or by following a common sense pattern, just by relating quantities. As soon as you have an equation or a system of equations, you just need to solve it. And most often solving is not a big problem because you are already quite good in it. So the majority of the work for the word problem is hidden here. How to organize your data, realize what kind of situation we play with, recognize some pattern, and finally write the equations that will allow you to solve for the variable. So solve the equation or the system of equations. Finally, when you already have the solution, it's a good idea to check if this solution is reasonable, if it makes sense. So if you end up with 58.5 people going for a trip, then obviously something is not quite right. Or if you end up with a negative time, that something is wrong and you need to double check what's wrong. So remember to check if your solution makes sense. As soon as you realize that basically everything looks okay and the solution makes sense, read again the question in the problem and give the formal answer. This doesn't have to be very long, but it should be some sort of formal answer, a short sentence or a phrase. So keeping all those points in mind, let's solve some typical problems. The first example will be from geometry problems. Here we have a building casts a shadow 20 feet long. A person 6 feet tall is walking directly away from the building toward the edge of the building's shadow. How tall is the building if the person is 15 feet from the building when the shadow of the person and the shadow of the building line up? We do have a diagram here that helps you visualize the situation. If we wouldn't have this picture, we will have to do it on our own. When you read the question second time, try to focus more on the data given. A building casts a shadow that is 20 feet long. You may want to even circle the data to bring it more to your attention. So let's identify this distance 20 feet on the diagram. This is the shadow of the building, which is from here to there. So this is 20 feet from here to there. A person 6 feet tall is walking directly away from the building. So here we have a person 6 feet tall. That's how high the person is, 6 feet here. And it's walking that direction, 6 feet. How tall is the building? So now the question asks us for the height of the building. That means this distance. And let's introduce the variable for this height. That will be h. The person is 15 feet from the building. So the distance from here to there is 15. Since we work with similar triangles, therefore we can apply similar triangle theorem. This is called Thales theorem. What Thales theorem says? Well, if you have two similar triangles, let's say I mark the small triangle in blue, and let's side of the small triangle be called ABC, and a big triangle in red, and let the side of the big triangle be called correspondingly capital A this side, capital B this side, and capital C this whole side here. Then Thales theorem says that the ratio of corresponding sides, for example A over small a, is the same as the ratio of B that corresponds to small b, and is the same as the ratio of capital C over the small c. This theorem you can always use when you deal with similar triangles. What are similar triangles? Well, similar triangles are those that will have the same angles. So in our case, this is a common angle, so obviously it's the same. These two lines are parallel lines, therefore these angles are the same. And these two angles are also equal because they are corresponding. So let's come back to our question. At first we introduce the variable, let h be the height of the building, and then we need to set up the proportion of corresponding sides. So let's start with h, that corresponds to the height of the person, which is 6, equals, and now the base of the big triangle, which is 20, corresponds to the base of the small triangle, which is just here, just this part. So this part is the same as 20 minus 15, which is 5. So 20 divided by 5. As soon as we have this proportion written, this solving it is quite easy. We start with h, we multiply across 6 and 20, so 6 times 20, and we divide by the third number, which is 5. Here I would suggest that instead of multiplying, you reduce, because then you play with smaller numbers. So it's just 6 times 4, which is 24. So your final answer is 24. And we need to give the formal answer. The building is 24 feet tall. The next problem refers to business problems. In business problems, we need to remember that a profit is the same as revenue minus cost. Revenue is all money that we can get from selling some items, and cost is the cost of producing these items. So the difference between revenue and cost is our profit. Let's see the example. It cost a manufacturer $8.95 to produce sunglasses that sell for $29.99. How many pairs of glasses must be sold to make a profit of $17,884? So how can we make sense of this problem? Well, we have given the overall profit of selling some number of sunglasses. We don't know this number. How many pairs of sunglasses? That's the number that we are looking for. So maybe let's introduce the first variable. Let n be the number of sunglasses sold. So we have a profit, and we can follow the formula profit equals revenue minus cost. So profit $17,884 equals revenue. But what is revenue of selling n pairs of sunglasses? Well, it will be the price of one pair of sunglasses times n. So $29.99 times n. Price per one pair times number of pairs gives you the total revenue. So this is revenue. And that one was profit. Profit equals revenue minus the cost. But the cost of producing one pair of sunglasses is $8.95, and we have n pairs. So the overall cost is $8.95 times n. So this one will represent our cost. And we have equation, so we just need to solve this equation. When you subtract $29.99 minus $8.95, you end up with $21 0.04n, and here we have our profit 17,884. Now finally, to solve for n, we divide 17,884 by 2104, and the final answer will be 850. So we can give the final answer: the manufacturer must sell 850 pairs of sunglasses to obtain desired profit. The following example refers to investment problems. When we deal with investment problems, it's a good idea to keep in mind the formula. Interest is principal times rate times time, PRT. Let's read the question. An investment of $2,500 is made at an annual simple interest rate of 5.5%. How much additional money must be invested at the annual simple interest rate of 8% so that the total interest earned is 7% of the total investment? So what we have here, we invest $2,500 at 5.5%, and then we want to invest additional money. Additional money, well, we don't know how much. That's exactly the question. At 8%. And the overall interest from both investments should constitute 7% of the overall investment. That means this 2,500 and additional money that we don't know. So let's introduce the variable for the additional money. Let x represent the amount of money invested at 8%, this amount of money. When you deal with investment problems, it's a good idea to refer to the diagram as follows. Start with the total investment. What's my total investment? Well, it is the $2,500 that we originally invested at 5.5%, and also the additional investment that we assigned to be x. Now, this money is split into two accounts. We invested $2,500 at 5.5%, and the rest of money, x thousand of dollars, we invested at 8%. So how do we calculate interest rate? Well, the interest rate, as the formula says, is the principal times rate times time. We're talking about annual interest rate, annual simple interest, so we don't want to worry about time. The time is 1 year. Therefore, we just multiply the principal times rate. Change the rate into a number, so it's 0.055 times 2,500, and then the interest from second investment is 0.08 times the principal x. We're adding those two interest rates, and this is supposed to be equal to 7% of the total investment. So 7% is 0.07 times the total principal, which is 2,500 plus x. So that's how you create your equation, and the rest is just to solve it. So when we multiply the first two numbers, it ends up to be 137.5 plus 0.08x equals 0.07 times 2,500 is 175 plus 0.07x. Now let's put all the x's together on one side. So you really have 0.08 minus 0.07, which is 0.01x, and 175 minus 137.5 is 37.5. Finally, we divide 37.5 by 0.01, and we end up with $3,750. So we're ready to give the final answer. $3,750 must be invested at 8% to make sure that the overall interest will be 7% of the overall investment. In motion problems, you always refer to the formula rate times time equals distance. So that's a golden rule to remember. Rate times time equals distance. Let's read our problem. A car traveling at 80 km per hour is passed by a second car going in the same direction at a constant speed. After 30 seconds, the two cars are 500 meters apart. Find the speed of the second car. We know we are talking about two cars. One car is traveling at 80 kilometers per hour in the same direction as the other car. The other car is traveling with a constant speed that is unknown. And the question really calls for this particular constant speed. Find the speed of the second car. So we're going to introduce a variable that will represent the speed of the second car. We can choose a letter v to represent velocity of this car. So let v be the speed of the second car. Speed and velocity, in our case, it actually is the same. So we can use both words interchangeably. V is our velocity of the second car. Let's make a diagram how this situation looks like. We have a first car that goes in certain direction, and then second car is going in the same direction. At certain point in time, for example here, the second car passes the first car. So at this particular point in time, they are at the same place. And then the second car is going with certain speed. Let's say in 30 seconds it may go up to here. So from here to there we have 30 seconds elapsed time. But during this 30 seconds the first car is also moving forward, but maybe not so far. So the distance from the position of the first car after 30 seconds and the position of the second car after this 30 seconds is the difference between the two cars. The two cars are 500 meters apart, so this distance is 500 meters. To deal with motion problems, I always suggest to start with the table rate times time equals distance and try to fill up this table with the data given. In our case, we need the first row for the first car and the second car. So what do we know about the first car? We are going to investigate just this part of the trip because we need the starting point in time to be the same. So what do we know about the first car again? Well, the rate of the first car is 80, that's for sure. And watch the denominations. This is kilometers per hour. So our time should be in hours. Our distance should be in kilometers because that's kilometers per hour. The time for this part of the trip is 30 seconds. So first of all, we need to convert the time to hours. 30 seconds. To convert to hours, you multiply by the converting factor that will have seconds in the denominator and hours in the numerator in order to cancel seconds, right? So 1 hour is the same as 3600 seconds. Therefore, overall, when you reduce 0 and divide by 3, that will be 1 over 120 of an hour. You also reduce seconds, so you end up with hours, right? So 30 seconds is the same as 1 over 120 of an hour. Okay, we can plug it into the table here. 120. This time refers to both cars. Both cars are driving for 30 seconds, which is 120 of an hour. The rate of the first car is 80, the rate of the second car is unknown, is v. So we can mark this box by v. Okay, now what we know about distance? Well, we follow the formula rate times time equals distance. So let's multiply 80 times 1 over 120. When you multiply, you can reduce the 0 and you have really 8 over 12. but that simplifies by 4 to 2/3. So the first car, during the 30 seconds, drove 2/3 of a kilometer. The second car drove V over 120. You multiply this times this, right? V over 120 kilometers. So now to make an equation, we are looking at these two distances and we know that they differ by 500 meters. Again, since we need to have the same denominations, the 500 meters needs to be converted to kilometers. That's 1/2 of a kilometer. So the difference in distances will be 1/2 kilometer. Usually in such table, the third row is about the total distance, but in this case it's about difference in distances. So this difference is 1/2 kilometer. To set up the equation correctly, we need to start with the longer distance. The longer distance is of the second car, and the distance of the second car is in this box. So we start with V over 120, and then we subtract the distance covered by the first car, which is 2/3. Overall, this difference should be 1/2. Now the rest is not too difficult because we just need to solve this rational equation by multiplying by LCD. LCD in this case will be 120. So let's multiply by 120. This means that we multiply this term by 120, that cancels 120. That term by 120, that cancels with 3, leaving us with 40. And finally this term by 120, that cancels with 2, leaving us with 60. So the final equation will be V minus 2 times 40, which is 80, equals 60. So V by itself is 80 plus 60 is 140 kilometers per hour. So the second car was really fast. It was speeding. And we can give the final answer. The speed of the second car was 140 kilometers per hour. The following example refers to mixture or solution problems. In this type of problems, keep in mind the formula percent times the volume gives you the content. For example, if you have the solution of salt, the percent of the volume will give you the amount of salt. Here we have a following problem. A radiator contains 6 liters of 25% antifreeze solution. How much should be drained and replaced with pure antifreeze to produce 33% antifreeze solution? So we see this is a solution type of problem. The question is, how much should be drained and replaced with pure antifreeze? So how much of pure antifreeze do we need to use to produce 33% antifreeze solution? Let's introduce the variable. Let X be the volume of the pure antifreeze. And we are going to stick with the table that refers to the formula percent times the volume equals content. We have two liquids, 25% solution and the pure antifreeze that we use. So reading again, a radiator contains 6 liters of 25% solution. So we can fill up this box. 25% is 0.25. The volume of this solution will be, originally it was 6 liters, but we are going to drain this solution and replace with pure antifreeze. So the amount of pure antifreeze that we use is the amount of the 25% solution that we have to drain. So we are getting rid of X liters of this solution. So the volume of it will be 6 minus X. Therefore, the content is the product of the percent times the volume. So 0.25 times 6 minus X. Now, when we look at the pure antifreeze that we use exactly X liters of it. That's exactly the same amount as it was drained from the 25% solution. Pure antifreeze means 100% solution, so this number will be just 1. And when you multiply, you have just x. The overall solution should be 33%. So we have 0.33 over there. And the overall volume is the volume of the 25% plus the volume of the pure antifreeze. So when you add it up, it's actually 6 liters. We still keep the same 6 liters. We just changed part of the original solution and replaced it with the 100% antifreeze. Therefore, the content of the overall solution is 0.33 times 6, which turns out to be 198. Now, in this type of problems, the equation comes from comparing the content. So the content from the first part plus the content from the second part, which is entire x, is the overall content in the solution. So we can write the equation 0.25 times 6 minus x plus an x equals 198. Now when we open the bracket and multiply 25 times 6, that gives us 1.5 minus 0.25x plus x equals 1.98. Now 1x minus 0.25 is 0.75x, and 198 minus 1.5 gives me 0.48. And finally divide, so that's the same as 48 over 75, because you can move the dot 2 places. And this could be simplified to 16/25. That's when you reduce by 3, which could also be given as a decimal as 0.64 of a liter. So a little bit more than half a liter needs to be replaced. And we can give the final answer. 0.64 liters of 25% solution must be replaced by pure antifreeze in order to obtain 33% solution. The last type of problems that we are going to refer to will be work problems. In work problems, we are going to multiply rate times time and obtain the amount of job done. Usually this is 1, but not always. So the work problems work very similarly to motion problems. You still have rate of performing the job. Rate times time equals usually 1. The amount of job serves like distance in motion problems. In work problems, we're going to add rates, but not times. In motion problems, we usually add times or distances or compare distances, but not rates. Here in word problems, we will always think about adding rates, or at least comparing rates, but not times. So here's our example. David can paint a house in 12 hours. Bill can paint the same house in 9 hours. How long would it take them to paint the house together? Well, the job to do is to paint one house. So that's one job to do. We know that David can do it in 12 hours, Bill can do it in 9 hours. We know the times for each person. And the question is, how long will it take them to paint the house together? Well, let's introduce the variable. So let's t be the time needed to paint the house together. And we're going to stick with the table similar as with motion problem. Rate times time equals job done. Instead of distance, you have the amount of job done. In this case, it's about painting the whole house, so it will be the same one job to do for David, Bill, or when they work together. So how do we fill up this table? Well, let's look at the data that is given. We have 12 hours for David, so he needs 12 hours to paint the house. Bill needs 9 hours to paint the house. When they are together, we don't know, so that's your t hours to paint the house. To get the rate, because remember, we are going to add rates. To get the rate for each person, we follow this formula, so we divide job by time. Therefore, here we have 1/12, here we have 1/9, and over there 1/t. That's how you create your equation. So let's write down this equation. 1/12 plus 1 over 9 equals 1 over t. That's a simple rational equation. We are going to solve it by multiplying by LCD. LCD in this case is 36t. So when you multiply, 36t will be divided by 12, leaving us with 3t. Then divided by 9 gives us 4t. And finally divided by t leaves us with 36. Now we can add, so it's 7t equals 36. And finally t is the same as 36 over 7, which is 5 1/7 of an hour. So a tiny bit more than 5 hours. And we're ready to give the final answer. It will take them 5 hours and a bit, 5 1/7 of an hour, if they work together. If we're curious about this law a bit, we can always convert it to minutes. 1/7 of an hour is the same as 60 over 7 in minutes, and 60 over 7 is approximately 8.6 minutes. So together they should finish the job in about 5 hours and 9 minutes. The last example is also a work problem. Here we go. A tank can be filled in 9 hours and drained in 11 hours. How long will it take to fill the tank if the drain is left open? And let's introduce the variable for what the question asks. How long will it take to fill the tank if the drain is left open? Let t be the time needed to fill the tank if the drain is left open. Again, let's stick with the table. Rate times time equals job done. So filling the tank is one job to do. Filling in takes 9 hours, so we plug it in 9 to this box. Draining out takes 11 hours, so 11 goes into this box. How long will it take to fill the tank if they work together? We don't know. That's our t time. And then we translate the information into rate of performing the job, rate of filling the tank. So it will be 1 divided by 9, job divided by time. That's your rate, 1 divided by 11 and 1 divided by t. Your equation comes as usual from comparing the rates. But how do we compare them? Well, filling the tank is a positive rate, but draining it out, it's actually a negative rate because it's undoing the work. It's not helping to fill the tank, it's draining it, so it's undoing the filling. So we can write the equation by comparing the rates. The rate that is helping to fill the tank minus the rate that is draining the tank equals 1 over t, overall rate. Now we solve it the similar way as before by multiplying by LCD, which is 99t. Then we obtain 11t minus 9t equals 99. Therefore 2t equals 99 and 1t is 49.5 hours. So it will take 49.5 hours if the drain is left open. So those are all examples that I can show you at that time. Now you need to practice a lot of questions. You may want to refer to these patterns that I showed you. But basically, the more questions you do, the more experienced you are, and it's easier to solve word problems in the future.